Alright, so as promised, let us go ahead and write, based on the most general relation, epsilon equals the compliance S multiplying the stress, 6 by 1, 6 by 6, 6 by 1. Let us go ahead and write the explicit form of S for the case of anisotropy. For the case of, I'm going to call it full anisotropy. Full referring to the fact that I'm not going to make any assumptions on the constants that appear in the compliance matrix. So I'll go ahead again, I won't be lazy and write out everything that has to do with the stress-strain relation. So we have stress versus strain, and I'll again split it up into, let me be brief, a normal components, shear components, and then this is going to be normal shear to, normal to normal coupling, couples shear components of the stress to normal stresses, normal strains, normal to shear coupling. This submatrix is going to ultimately couple the shear strains to normal stresses, so this is Sn, and finally this is shear to shear coupling, couples shear stresses to shear strains. So this is 6 by 1, this is 6 by 6, this is 6 by 6, let's remember those. This is a 3 by 3 matrix, 3 by 3 submatrix, 3 by 3, 3 by 3. Okay. So first we have the stresses sigma x, sigma y, sigma z, and then tau yz, tau zx, tau xy, and here we have epsilon x, epsilon y, epsilon z, and gamma yz, gamma zx, gamma xy. Good. So now I want to write the relation between stress and strain in its most general form. And in this most general form, I'm going to discard the notion that only normal stresses influence normal strains and only shear stresses influence shear strains. Which means that I should probably not think of these components as being zero. They do not have to be equal to zero. They can actually be anything. So these won't be zero. And in general, for the case of isotropy, for instance, you've seen that this subblock, this submatrix, this block was diagonal. In general, I'm going to discard also the notion that only tau yz, say, influences gamma yz. So off-diagonal components of this submatrix, they are also going to be admitted as being possibly non-zero. So in other words, I'm going to write the full 6 by 6 matrix. So let's go ahead and do that. I'm going to write the diagonal components first, just as a guide to what we're doing. And we typically just enumerate those components instead of using x, x, y, y, z, z type of thing. So 1, 1, 2, 2, 3, 3. So this is going to be S4, 4, S5, 5, S6, 6. So this one multiplies that, delivers that, but the other components here are also not going to be zero. So let us write those also in red. So this is going to be S12, S13, S23. This is S31, S21, sorry, S31, S32. And here I will have S45, S46, S54, S56. Okay, now I'm not admitting anything to be 0, so I'm also not going to admit any of these to be 0 either. So I am going to go ahead and write those as well. So this is going to be S14, S15, S16, S24, okay, a little cumbersome, but it is worth the effort for subsequent discussion. S63, okay, and there you go. And what you see is the full complexity sort of almost is a mess, and we see 36 components fully written, and now what I see is the full coupling between the normal and shear components of strain and stress through the matrices NN that govern NN, NS, SN, and SS coupling. Okay. So now what we see is, suppose you have a scenario where you have only shear stresses and no normal stresses. These are 0. These would multiply, for instance, the first row, and these are non-zero, and hence you would get a normal strain out of it, etc. So the fact that you have these eventually causes that behavior that is distinct from the case of isotropy. And moreover, I seem to have 36 components. Now, so there are 36 components, but it turns out, and I already gave a hint, it turns out if you have normal shear coupling, you have to have shear normal coupling. And that is a consequence of something that is a little bit more general with respect to the structure of this matrix. And we do not need to ultimately memorize anything that has to do with the components of this matrix for some special, let's say, form of anisotropy, not necessarily full, but we have to always remember that this matrix is importantly symmetric. Okay? Now, the compliance matrix is symmetric, and remember that there is the alternative form that I can write over here, and the alternative form is the stiffness matrix. So sigma is equal to stiffness multiplying strain, 6 by 1, 6 by 6, 6 by 1. So that's the alternative form, and therefore, since C is the inverse of F, if S is symmetric, then C is also symmetric. So both of them are symmetric. Okay, but focusing to compliance, it is a symmetric matrix. So the question is, how many independent components does it have? So in other words, if I give you a material and you want to work with it, and I tell you it is anisotropic, and it has full anisotropy, meaning there is no special relation between any components. So for instance, isotropy is a subset of full anisotropy. And therefore, I just need to give you two components and I tell you it's isotropic and you know how to work with it. But even then, if I give you just two constants and if I don't tell you that these are 0, you wouldn't know that the material is isotropic. You would know that there's some information that's missing. If I give you just E and nu, I have to also tell you that the material is isotropic, so you figure out that these are 0, etc. So the hint of isotropy tells you a lot about the structure of this matrix. So now if I don't tell you that information, I don't give you that information, and I tell you, okay, the material is anisotropic, so I want you to work with it, I give you a stress, you need to give me what the strain is. The question is, how many constants should you ask for to be able to do that calculation? In other words, how many values do I need to supply to you so that you can know the full form of the compliance matrix? And the answer is, think about it. There are 36. Do you need to know all 36 is symmetric? No. The answer is 21. Why? Well, subtract the diagonal components. This upper triangular matrix is the same as lower triangular. So 36 components, subtract the diagonal 6, 30, divide by 2, 15 there, 15 there. I can take any 15, let's say that 15, add back the diagonal, 21. And therefore, I know everything about the matrix. So 21 independent components. In general, okay? In general meaning in the case of full anisotropy, there are some special cases in which I don't need 21. You tell me that there is a very specific type of anisotropy and I give you its name along with all the constants that you need to know about that special case of anisotropy, say only 3, and then you know its explicit structure. Or I give you only 9 and I tell you that it's of this special form of anisotropy and you know exactly what its structure is. Just like I give you only 2 and I tell you it's isotropic, you know the full structure of the compliance matrix. But in general, if I don't tell you anything, I need to provide you with 21 independent components, which is sort of cumbersome, but that's the way it is. So if you need to do experiments to characterize a material behavior, I give you a material, you know absolutely nothing about it, it's been just manufactured or it's given to you and you're asked to work with it, but nobody tells you the type of material behavior it displays. So you have to go ahead and do experiments, determine the full form of this compliance matrix, and then looking at its structure, you can deduce whether it fits into some special form of anisotropy or it is in its full generality, or perhaps you're lucky and it comes out to be isotropic, okay? So, but that you recognize by looking at the form of this matrix, the compliance matrix, which will have 21 independent components, okay? All right, good. So, why is the matrix symmetric? Now, we can remember, why is the stress symmetric? Well, because the angular moment, the moment balance needs to be satisfied for an infinitesimal element of solid under the action of those stresses. So that's why it's symmetric. Why is the strain symmetric? Well, because gamma yz means the angle change that has to do with lines along y and z axis, and that angle change doesn't depend on whether I look at y versus z or z versus y. The angle change is the same, so it's symmetric. So from 9 we go down to 6, from 3 by 3, 9, we go down to 6 independent components. So here we have 36. Why do we have 21 independent components? And the answer is something that we could rigorously look at mathematically, but let me just describe you in words why the compliance needs to be symmetric. And our discussion is going to be a simple discussion that is based on, again, the example that I like to give. We just take a cylinder, solid cross-section, say, and I will do some experiments with it. And the first experiment I do will be, well, remember the concept of strain energy. Suppose I pull on this cylinder with an increasing force. This thing will elongate. And then I increase the force, the more elongation. And as it elongates, it stores a certain amount of strain energy due to the elastic deformation of the cylinder. And if I then remove the force slowly, that amount of elastic deformation will be ultimately recovered and it will go back to zero deformation at zero load. And so when I load it, it slowly stores energy, strain energy, and if I unload it, it will reduce the amount of energy that is stored in it. And now the question is, what is the net work that I do when I pull on it and then I release it? So in other words, when I go through a cycle of loading and then unloading, what is the total strain energy change within the elastic cylinder? Now, for that matter, I can ask the question of a torque. Suppose I torque this thing. The more torque, the more twist. I do some work, and then I slowly release the torque so it twists back, and then I ask you the question, what is the net change in the strain energy when I start from undeformed state, go to deformed, and then I go back to deformed state? Or alternatively, what is the net work that I do? Or finally, I could have had a bending moment and I could apply a bending moment. And this thing would bend, and then the more moment, the more bending, store some strain energy, and then I release the bending moment, and then it would go back, and I ask you the question, what is the net work that I do, right? So, and the answer in every case, your expectation is that the net work I do should be zero, right? I pull on the elastic cylinder. So when I pull in that direction, it extends in that direction, and then I slowly reduce the amount of the load. So I don't push, I don't need to push, I just release the amount of force I apply. It's always in that direction, it just goes back to zero from a positive value. But now the motion is in the reverse direction, so the work that is done is negative now when I unload. So loading is positive work, unloading is negative work, and then the net work should be zero. That's your expectation. Why? Because that is ultimately defining your, or fitting your definition of an elastic material behavior. So an elastic material behavior is one where you expect, and in fact this argument is irrespective of whether the deformations are small or not, but the argument is that elastic behavior is associated with zero net work over a cycle of deformation. Now, why is that specific to elastic behavior? Well, because if I deform something plastically, I know that after I remove the load, there's a certain amount of deformation remaining. And in fact, I know from experience that deforming something plastically can require a lot of work. I feel that I put work into breaking something, into deforming something permanently. Whereas that's not the case with elastic deformation. You take a spring, you extend it easily, gives back all its strain when you remove that load. So you don't feel as though you're doing as much work, and in a theoretical setting, the work you do, of course, would be exactly equal to zero. So for a cyclic variation of stresses to deliver you exactly a deformation such that load times deformation integrated over a cycle, okay, so that's work. So that work over a cycle is equal to zero. For that to be observed, and that's my physical expectation, it turns out this matrix needs to be symmetric. If it's not, you apply a stress, you get a deformation, and you keep calculating the amount of incremental work you do. You sum them up over a cycle. If this is not symmetric, you'll end up with a net work. Where did that work go? Well, it's unphysical. That's not something you expect, and therefore the matrix needs to be symmetric. And that's why if a material, an isotropic material, displays normal shear coupling, you expect it to display shear normal coupling as well. All right. So as a consequence of symmetry, notice S5,4 is equal to S4,5. This one is equal to that. That's equal to that, etc. So S2,4 is equal to 4,2. So just like in general, the components of the shear stress and the shear strain, when you switch the indices, the result doesn't change. It's the same with this matrix. When you switch the indices, it doesn't make a difference. 4,3 is the same as 3,4, etc. Okay. So that is our full form of the compliance matrix for general anisotropic material behavior. And now the idea is to look at a few specific cases.